Hello, my name is Nir Keren. I'm from Iowa State University. I'm going to present instead of a high level, which will be the topics that we see in in other sessions. I've decided to go and look at a more specific example of how I use virtual reality to solve a problem. So my presentation title is VR as a platform for developing systems mental model in technology students. Just a little bit of a background for me. I served as an engineer and a manager in energy capital facilities for more than a decade. I'm currently a faculty of occupational safety in the Department of Agriculture and Biosystems Engineering at Iowa State University. I'm also a faculty fellow at the Virtual Reality Application of Visual Application Center at Iowa State University. And one of the courses that I am teaching is risk analysis and management, which is essentially system safety engineering. So why pursue system mental model in virtual reality? So with my vast experience, when I talk to students in my course about systems, this is the type of responses I'm getting. The deer in the headlight response came through quite often. And it made me think a little bit about why this is the case. And when I pursued my thoughts further, I noticed at the bottom, we can see the way systems are being portrayed to students in engineering and technology cases. Sometimes we'll have a 3D representation of the systems. And then when they come to work in the workforce, the system they see is at the top. It takes a major bridge efforts in order to get into a level when you can understand the system at the top, which is exactly what the mental model will present. So my question was whether I can use virtual reality in order to supplement and give experiential type of learning to students that will allow to enhance their mental models of industrial systems and better prepare them for the workforce if they need to work with systems. So just to put us on a playing field, when I'm talking about mental models, I'm referring to the internal representations of us and the world around us in a way that guides us on making decisions and acting upon the world. So there is a lot that can be said about measuring mental models, and measuring mental models is not for the hard-fainted. For our specific case, we look at the mental model of mechanics systems, which the Clear and Brown developed to sub 4 notions of device topology, envisioning, causal model, and simulation. Device topology looks at each component in the system as independent. Envisioning is the notion of what each component is doing in its local fashion. So a pump generates low pressure at one end, high pressure at the other end, and it creates a flow. Causal model is the general perception of how the system is operating, what its goal, what is that comes at one side and what is coming outside without knowing the ins and outs of the system. The final notion is simulation. Simulation is an advanced notion that requires vast understanding of the model to a level when it's possible to predict how the system behavior based on changing conditions. For our perspectives, as in system, we talk about major components in the system. We divided the device topology or system topology to sub-notions of process topology, which is the major components of the system that facilitate the process: a chemical reactor, a major heat exchanger, feeding into the system. These are process topology. And then service topology will be the items that service, like a pump that is in place, a compressor that provides the air, and so on. The reason for this distinguishing between these two is that a vast experienced person can go into a system, look outside, identify the process topology, and can tell what the system is doing, but without knowing what the service topology of the system is. So how do we pursue assessment of the enhancement of mental topology through VR? So we've developed two virtual reality environments for the study. One of them is a cooling water system that we can see here. The system is quite simple. There is a tank, there is a chemical reactor, and there is a cooling water tower, and there is a pumping system connected with them, including pipes, pumps, some filters, and valves, and students can go around in the system in full scale and interact with them. They pull a component out, looked at it, examined it, and they will leave it, and it will go back to its place. And the other system that we developed is called the System Designer VR, or SDVR. In this element of the study, in this virtual reality environment, students have been presented with a problem statement that is available on the wall, as can be seen in this area here. And there is a boiler room, and students could build the system in order to solve the problem that is provided to them. Next, we're going to see a video that shows how the System Design VR is working. Hopefully, this will play. I'm sorry. Going back, my apologies for this. So if we go back to the System Design VR, the experimental design was as follows. We divided the students to two groups, the pre-group and the post-group. In the pre-group, students interacted with the pre-built cooling water system, and then went and built System Design VR. In the post group, the system first built the system in VR and then interacted with the pre-built cooling water. And we compared the mental model of the students immediately after the cooling water, whether it's in the pre or the post group. Again, we had 33 undergraduate students. We divided them to two groups, as mentioned. We gave them a VR tutorial to get rid of the GWIS, if you want, so the novelty of virtual reality will not be in place. We used the Oculus Quest 1 as a system for this. Just two examples of a system. That's the boiler room before the students begin to work. They have to provide hot water that are clean to a water supply here on the left, and then collect the cold water that comes from customers, cool them, and put them back in the boiler. Example of a system that one student built is here. It's very nice, very well organized, and very clean, considering all the aspects of having two pumps in place, one filter, and how the system is working. One of the students, and only one of the students, built the system along the walls, and he has no experience whatsoever about with system design. He just had the hunch that he shouldn't use the entire space because it can be used for other things. Just an element of the mental model that is not being well presented. So now we assess the change in mental model. When we look at the process system topology, which is the global elements of the process and what the students remember and what their functioning are, we noticed that there was a moderate, a weak significance, but it was there, and effect size was actually moderate. Similar thing when we look at the service system topology, the valves and the elements that helps the process but not facilitated, we had a moderate weak significance and even a little bit larger effect size. Envisioning is when each one of the components in the systems and its functioning, there was no difference among the groups. Causal model, which is the global understanding of the system without knowing the ins and outs, we had a significance. The effect size was quite large. We did not see any significance on simulation, and that was expected because in simulation there is a vast understanding of the system in place, and this was not facilitated with this short interaction they had with this. We, looking back at the mental models, we believe based on our understanding that maybe envisioning is not really a factor in the mental model. We will conduct factor analysis on the data we'll collect further with the system in order to understand it. So reflecting on the results, the Clear and Brown, when they talked about teaching system mechanistic systems for mental models, they look at three types of learning. In the first type of learning, there is an understanding of relationships between the components of the system and their functions. This is what we call the process and service system topology. We noticed there was a marginal improvement and there was significance. In the second type of learning is the point where students convert implicit assumption into explicit assumption and form the relationship between the elements in the system and the general performance of the system. That's what we call the causal model, and there was a significant improvement on this second type of learning. In the third type of learning, all this causal model and all the service topology, system topology, envisioning need to be harnessed together in order for the students to predict how the system behavior under various conditions. There was a short exposure here. We did not expect to see any significant difference in the notion, and we really did not find any significant difference. In summary, the result shows that there is a potential for VR application such as the System Designer VR to serve into developing a mental model in one session only. Only in one session we were able to make a shift in three of the notions. I would say, though, that the shift went from being between poor to fair and fair between good. Very good wasn't placed, but this was only one session. We are planning to implement conduct a longitudinal study in order with the various exposure throughout academic experience for these students in order to see what merit does a system like System Design VR can provide as an experiential tool that enhances mental models. Thank you. And if there are any questions, I'll be happy to share.